So we talked about the law of inertia. Can you go to this page here, please? Here's the short version of Newton's first law. If an object is accelerating, there must be an unbalanced force acting on the object. But it also works in reverse. If there is an unbalanced force acting on an object, the object must be accelerating. There's not many laws that work both forwards and backwards. In math, we call these if and only if statements. And anytime you come across one of them, your eyes light up because you say, oh, so if I prove one side, I've automatically proved the other. I don't need to prove both sides of this statement. I like that. Little note, acceleration can mean changing your speed, speeding up, slowing down, but it can also mean changing your direction. Like when you go around a corner in a car at a constant speed, you are accelerating because you're changing direction. I told you that force was a vector. Put your pencils down. Let me pause the video here. So, how does Newton's first law help explain how seatbelts save lives? If the seatbelt wasn't there, what would happen? You want to keep going, here's the phrase, in a straight line at a steady speed. Newton's first says you want to keep going in a straight line at a steady speed. So what the seatbelt does is it prevents mass from moving in a straight line at a steady speed. All Newton's first law says is objects, again, Alicia, Newton phrased it, objects at rest tend to remain at rest, objects in motion tend to remain in motion, which is really confusing. It's that old English style. What I'm telling you is anything with mass resists change. In fact, I told you that inertia could be thought of as the laziness of an object. So if your body is moving at 60 kilometers an hour due north, it wants to keep moving at 60 kilometers due north, and the only way to prevent that is to apply an unbalanced force, the seatbelt. The seatbelt. To apply an unbalanced outside force. By the way, what's the front seat called? What do you call out when you want the front seat? Come on, guys. This is why the front seat used to be called, the reason you guys yell out shotgun is that was the nickname for the front seat before seat belts became mandatory. If you were in the front passenger seat and the car was in a collision, the running joke was you'd be the first one out to inspect the damage because you'd go through the windshield and on your way past the front end, you'd say, oh, you got a damaged bumper. Of course, you'd be dead. But that was the morbid graveyard humor. Have you ever wondered why you guys yell out shotgun? Why would you yell? Because of that. It's Newton's first law. Hashtag nerd trivia. So let's do some questions, some thought experiments. Okay? You don't just yet realize just how powerful Newton's first law is, especially if you know an object is at rest and not accelerating. So number one says, Manuel weighs 1,000 newtons. That means gravity pulls down on him with 1,000 newtons of force. And he stands on a board that weighs 200 newtons. So how much force is there downwards, grand total? Do the math in your head, please. Alex, how much force is there in this picture downwards, grand total? Do the math in your head, please. Loud and proud. Is he sinking into the ground like quicksand? Say no. Is he flying into the air like Superman? Say no. So how much force is there down? How much force must there be up? Exactly how much? Alex, 1,200. This is Newton's first law. Alex, is he sinking into the ground like quicksand? Is he flying into it like Superman? Then the forces must be balanced. That's Newton's first law. And in fact, I can tell you it's going to be 600 newtons apiece from each scale pushing up. How do I know it's split evenly? Because he's standing dead center. What if he stands off center a little bit? So Manuel moves to the left as shown. Now the scale closest to him reads 850 newtons. What must the other scale show? Do the math in your head. 350, got to be. You don't realize until you start to, by the way, these are called free body diagrams. We're going to get into them. But Newton's first law, Connor, lets you identify forces that are missing, especially if you know an object isn't sinking into the ground like quicksand and it isn't flying into the air like Superman. Then you can say, wait a minute, I figured out what gravity is, but there's got to be something pushing up against gravity. Here's a truck. Now we'll go with tons. So a 12-ton truck is 1/4 of the way across a bridge that has a weight of 20 tons. A 13-ton force supports the right side of the bridge. How much force must the left side of the bridge support?
19.
Is he right? Alex can do math in his head. He's smarter than he looks. Oh, shoot. That's going to go on YouTube. Oh, I have 2 Alexes, so that nobody will know which one I'm talking about. Is that okay? This is Newton's first law. Newton's second law. Newton's second law is actually just an equation. It tells us how to calculate force. It turns out force equals ma, mass times acceleration. Hey, did we do a whole unit on finding acceleration? Yeah. So if you take that number, a equals vf minus vi over t, or a equals vf squared minus vi squared over 2d, or what? Anyways, all those equations with a, if you find a, multiply it by the mass of the object that's moving, that's how much force you would need to apply to move an object with that mass and that acceleration. F equals ma. It's one of only 2 equations for this unit. This one you'll all memorize because you'll get sick of looking it up. So you need to memorize this, even though it's on your formula sheet, but you need to memorize it, Alicia, because you're lazy and you don't want to look it up all the time, so you will. Note, oh, by the way, up here, so what's another expression for acceleration? Can you get the a by itself, please? What's the m doing to the a mathematically? Adding, subtracting, multiplying, or dividing? So how will I move the m over? So another way to find acceleration is force divided by mass. Yeah. Oh, and I guess, what's an equation for mass? F over a. Don't bother writing those 2 down in your sheet. I'm hoping you can glance at this and do the math in your head. Again, hopefully I've convinced you that this whole being able to rewrite equations is a nice way to go. So this also means that 1 Newton is actually, well, if it's mass times acceleration, what do I measure mass in? What units do I measure mass in? Kilograms. What are the units for acceleration? Technically, 1 Newton is 1 kilogram meters per second squared. And we used to use that, and then about 100 years ago they said, let's name that force unit after Sir Isaac Newton. Okay. So, Malcolm has a mass of 65 kilograms. What's the magnitude of the gravitational force acting on him? What's this question want me to find? I'm looking for a word that begins with the letter F. Force. Which force? Okay. My symbol for the force of gravity is an F with a little g, and I guess that's going to be ma, because F is ma. What's Malcolm's mass? 65. What's A of gravity? You all know this. Sorry? You all know it. Yeah, say it loud and proud. We're going to ditch the negative because I'm not, that's why I said magnitude. Okay? 9.8. 65 times 9.8. 65 times 10 is 650, so it's going to be a little less than 650. What do you get? 637 even? 637 what? What do I measure force in? Newtons. Or you could write kilogram meters per second squared. Most of you will choose just to put the capital N because it's way less writing. Okay. By the way, in physics, this force of gravity pulling you to the earth has a special name. We call it weight. Weight is not measured in kilograms. Weight is measured in newtons. Mass is measured in kilograms. And I've been very careful all year to use the word mass whenever I could. What's your mass? What's your mass? By the way, pounds is actually a unit of force in the imperial system. So your weight in pounds, that is correct. Did anybody know how you measure mass in the old imperial system? What are the units for mass? And you've all heard of slugs. I swear to you, that's what it was called. I hate the imperial system, and why we still use inches and feet drives me crazy. Let's just ditch all of that and go full metric, because powers of 10, it's way easier to do math with. Anyways, if I ever ask you for the weight of an object, I'm really asking you for Fg, the force of gravity. The space shuttle has a mass of that. It does. I looked it up. If each engine is capable of exerting a force of 12.5 meganewtons, which they are, I looked it up. A, what's the maximum acceleration of the space shuttle? What's this asking me to find? Now, normally when you did this, you would have then said, hey, did they tell me time? Did they tell me distance? Did they tell me velocity? Did they tell you any of those things in this question, Ryan? Hey, but I've learned today a new equation that has acceleration in it. Which one? Yep. Okay. So acceleration is a special physics quantity. You're going to find a number of ways to find it. And the message, Courtney, is look at what they gave you. That's going to tell you what approach to use to find it. Now, the mass is 2.03 times 10 to the 6th. The force is, first of all, how many engines are there?
25.
How many engines are there?
2.
So let's multiply everything by 2. What's one engine? 12.5 what? What does the capital M stand for? Mega. On your purple sheet, can someone look? What was mega the same as? 10 to the what? Okay. I did that just to remind you about your metric prefixes and all that stuff. And it's the space shuttle. I missed the space shuttle. It was pretty cool. So what will the space shuttle accelerate at? Let's see. Two times 12.5, and then I can replace a mega with 10 to the 6th, divided by 2.03 scientific notation button 6th. You might, I don't think I need to put the top and bottom in brackets, but your calculator might require you to. It's all, this is the time you figured out how your calculator works. I get 12.3. Anybody else? Yeah? 12.3 what? Acceleration. Units. Meters per second squared. Turns out the space shuttle doesn't accelerate that much. If you want, it's only about 1.25 Gs. It's not a lot of acceleration. You'd notice it. I mean, it's intense. It's more than you're used to, because most of you, even like California Screaming, for example, only has an acceleration of about 6 meters per second squared. So about half that, if you've been on that roller coaster. B, why does the acceleration change as the engines burn? It does. It accelerates faster and faster and faster and faster and faster. Why?
It's forcing the plane downwards, which gives a force down on the newtons that are going up. So it creates an unbalance.
Nope, but that's going to be Newton's third law. Patience, I'm coming back to that. As you burn fuel, what happens to this number right here? What happens to the mass? Decreases. Oh, and so now you're dividing by a smaller number. If you divide, the force isn't changing because that's a constant flame, but if you divide by a smaller number, what happens to your answer? Gets bigger. Yeah. To be honest, if we wanted to analyze a changing acceleration like this, where the mass is changing, Alex, this is where we need calculus. I can't do it with any of the tricks that I've shown you. I could solve it very easily with calculus, but without it, I'm out of luck. But for what it's worth, mass decreases. Stop. Can I show you some good symbols? You know what? Don't write that down. Ready? Mass decreases, force. Can we use down arrow and up arrow for increases and decreases for the rest of the year? That's a good shorthand. I'll figure it out. Okay. How does Newton's second law explain why a sprinter would want to wear lightweight shoes? So some sports physics. Why does this explain why lightweight shoes are better? Which they are. What? Right? First of all, sprinting, it's all about the acceleration. Can we agree on that? Okay. Let's suppose, Rebecca, you're an Olympic sprinter. You've lifted weights, you've done steroids or whatever. You've maxed out your force. You've made the force as big as humanly possible. The force from your legs is as big as humanly possible. Well, how else can you change the acceleration? Connor. Because if you divide by a smaller number, what happens to your acceleration? Has to get bigger. Has to. Okay? So, as m increases, decreases, because there comes a point when you can't change the force. You've lifted weights, but Lindsay, this is why athletes work out and lift weights, because you can control that too to a degree, but it's not like, I mean, there's human limitations. Most of the world record changes in the past 15 or 20 years in most Olympic events have been equipment changes. Yeah.
Wouldn't the F and B be A then?
Sorry, what? Wouldn't the F in B?
Shouldn't it be A then?
Oh, I'm sorry. You're right. Scribble that out. Because the force is constant. Thank you. Candy for you. The engines don't put out more force, but as you burn fuel, your acceleration will then get bigger. By the way, you may have noticed that because if you ever watch the old videos of the space station take off, the rocket doesn't seem to be accelerating very fast at the beginning, but then later on when it seems to really be moving. Yeah, it's burned off a lot of its mass. Newton's third law. The trickiest one to work your brain around, but the coolest one, the one that will actually, by the end of today, convince you that everything that you thought about how you move or do things is totally wrong. Newton's third law is typically phrased, Hedrick, as, for every action there is an equal and opposite reaction. Huh? I've never really been able to understand that. Here's Mr. Dueck's version. You ready? Forces come in pairs. Forces come in pairs. That's Newton's third law. Or, if you want to do it, Haley, a bit more mathematically, the force of object A on object B is always the same as the force of object B on object A, except I'll put a negative in front because it's in the opposite direction. I'll show you some examples. So how does Newton's third law help explain why it's difficult to walk or drive on ice? By the way, what force makes a car go forwards? Are you going to say it's the motor? Convince me that it can't be the motor. That would mean as soon as you started the car up, the car would start moving forwards because that motor's running. What force is it that pushes a car forwards? Or why is it tough to drive on ice? Friction. We're going to spend a whole day looking at friction, maybe even longer than that. So how does Newton's third law help explain why it's difficult to walk or drive on ice? Since forces come in pairs, what? Let's look at walking. Shoe pushes back on ground. Ground must push forward on shoe. And if it's icy, the ground can't push forward very hard, so you're limited. This goes back to when I had Alex going to push against Jaden on the scale there. Alex, you might be able to do 700 or 800 newtons of force, but forces come in pairs. You can't if the other object can only apply 300 newtons of force. Again, it would be like trying to beat somebody to death with a feather. You're trying to apply a big force with a feather. The feather can't accept that big force. It's not going to happen. I just made that one up. That's kind of violent. I'll find a better analogy with the feather. Yeah. Give me 30 seconds. Some examples. Put your pencils down. How does Newton's third law explain why professional boxers need to wear boxing gloves? So if my fist is going to apply a force to Hedrick's face, what will Hedrick's face do? Which could, again, if I hit him hard enough to break bones, I must break bones in my fist. No, 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 no. If I'm a boxer, I wear gloves, right? So, how about F of hand to jaw equals negative F of jaw to hand. If I punch Hedrick in the jaw and I hit him hard, his jaw will apply exactly the same force back on my hand. So you couldn't if you were a professional boxer. And by the way, in real fights, it's why most often in a real fight, like a scrap somewhere, one of the consequences is a broken hand or two. You see it all the time among athletes who get into fights and practices and things. So-and-so is out with a broken hand. Yeah! Newton's third. Of course they are. In the collision below, which vehicle experiences the larger force? The truck, the car, or both the same? You know what? This is a chance for us to vote. How high you hold your hand up is how sure you are of the answer. I'm positive, I'm pretty sure, I'm voting because Mr. Dewick is keeping track and he'll make fun of me if I don't vote. So, we have a big truck colliding with a little car. Which vehicle experiences the larger force? Who says, Mr. Dewick, the truck experiences the larger force? No, Mr. Dewick, it's the car. The car gets Mr. Dewick, it's the car. Is that a hand? Who says both the same? Why? Why? Forces come in pairs. Now this bugs some of you. I can see Alicia, she's saying, okay, but because here's what you're wondering. So why is it that the car and the driver are almost always worse off after the collision than the truck? Yeah.
Truck is more inertia.
More mass. You know what? Same force. Let's go F equals F. But in the truck, let's put the truck right here. Let's put the car right here. I'll put F truck equals F car. But I would argue, Alex, for the truck, big mass, small acceleration, because F equals ma. I would argue for the car, small mass, huge acceleration. And in fact, we like to say in physics, it's not the force that does the damage. It's the acceleration that does the damage. It's the acceleration that does the damage. Okay? Homework. So part one, Newton's laws. There's lots of little questions here. We're going to fill in the first one together. It says, little Nellie Newton wishes to be a gymnast. She has a weight of 300 newtons. So right now, that weight you can fill in for part A would be 300 newtons. What if she hangs from two scales? What would each scale read? 150 and 150. So I'll let you think about the rest. Okay? Did I attach the answers? I think oh yeah, there's the answers at the bottom. Then, number 3 says, in the example below, the action-reaction pair, the forces come in pairs, is showed by arrows or vectors and described in words. So in A through G, draw the other arrow. Let's do A together. Head bumps the ball. What else can you tell me? If you had a soccer ball, what does the ball do? You can draw an arrow pointing that way. Who are my soccer players here? Anybody? So I don't know if you've noticed, Sarah and Jess, in the U.S., the U.S. Soccer Association, just this year, they've passed a rule. They're not going to let kids head the ball until I think they're 12 years old, because they are noticing a lot of college players are getting that whole football condition, ECE or whatever they call it, where your brain is damaged. They're starting to see it in soccer players, especially forwards that head the ball all the time. So they're saying, well, you know what? Maybe we shouldn't be letting them do it at that developmental age when they're 10, 11, 12, when their brains are still growing. And that's now mandated in all youth soccer in the U.S., probably becoming soon to Canadian soccer as well. Yeah. Okay. So I'll see if you can fill in the rest of them that way. Then, number 4 says, use Newton's second law to solve the following. Here's the mass. So, if I have 25 kilograms and I apply a force of 100 newtons, what will my acceleration be? Well, we have this. How would I get the A by itself? Yes? So that should help you, I think, for this mass of 25 kilograms. You can fill in all the missing stuff here. If you want to accelerate at 10 meters per second squared, how many newtons of force will you need? And then B is for a constant 50 Newton resistance. So now what we're saying is there's 50 newtons pushing that way, which means instead of, 50 newtons, what's your net force? If you have 50 newtons pushing this way and 50 newtons right, 50 newtons left, what's your net force? What's your net force right here? We did this in the notes earlier. What's your net force right there? 0. So what's your acceleration? That's what it's saying right here. What if I have 100 newtons to the right and 50 newtons left? What's my net force? Net force would be 50 newtons. I'll let you think about what the acceleration would be for a 25 kilogram mass. See if you can figure that out. Okay. Then, part 2, classify each of the following as examples of Newton's first or Newton's third, and you can simply write 1ST or 3RD or even 1 or 3. I didn't attach the answers for these. We'll go over these answers next class. You got 25 minutes. You can get all these done, and there's some nice thought-provoking questions here.